to track information from application into the database boundary.
Okay. Hi. Can you hear me? Great. So I'll be talking about joint work with Daniel Hedin and Andres Abelfeld, who are in the audience here somewhere as well. And the basic idea about this is to track, to do information flow control for programs that have both normal computation and do some database queries. So the basic problem is that we have a lot of confidential data on our devices. It could be location information, it could be financial records. And we give that data to quite a number of applications, which are not necessarily trustworthy. And these applications are pretty complex. They're like the typical web application would be composed of many different components. It would have normal code, it would have database queries and stuff like that. And often there's a problem when two components communicate and communication at the boundary isn't really done properly. One instance of this would be, for instance, SQL injection attacks or this sort of thing. So as a result, to handle this kind of thing properly, we need to look at security as an end-to-end kind of concept and need to look at the communication across the boundaries. And what I'm talking about here is based on work from last year's ICFP on language interface query. And this basically adds a security angle to that work. And in a nutshell, we give the following contributions. We track information flow for code that's using database queries. And to enforce that, we have a security type system ensuring a property called noninterference. And we implemented a type checker and compiled and a compiler which outputs F# code for our toy language that we're using to exemplify our approach. And then also we extended our system to handle algebraic data types and pattern matching and looking at the information flow properties for this. And lastly, we have a case study about a movie rental database to demonstrate some measure of practicality of our approach. So the overall idea is that I'll first outline how, so traditionally when you have SQL queries in an application, you write code in one language, then in that language you write some SQL queries as well, and it could be just a normal string that occurs in the language, that's the query, and then that gets run on a database. And if you sort of mess up constructing that query correctly, then you could have all kinds of security issues or even code that just crashes. So once again, this is SQL injections are one problem of this sort. And if you instead, so lately then people think like it would be nicer if this stuff were integrated into a language. We write the code in one language and then compile different parts to different output languages. So you would write just F# code, for instance, and then parts of it generate SQL queries, parts of it just get run normally. And if we are using this approach, then we can sort of use the compilation process to make sure that the communication is correct and doesn't introduce security issues. And now I'll give a bit of background on information flow control, since that's the kind of security that we are concerned about here. The basic intuition is that untrusted programs, they shouldn't leak private data that you give it to untrusted sources, even if the programs need access to the private data to perform their function. So this is becoming more and more relevant due to most people have smartphones that collect a lot of sensitive data, and then you have lots of apps that you don't trust. And the way to formalize what we mean that untrusted data isn't leaked to third parties is usually called noninterference. At least that's a useful baseline to start from. And noninterference basically works like this. You have some channels, you have some private input, and you have some public input. And then you have some parts of the output that are private and some parts of the output that go to public sinks. This could be data that gets sent across the network or something like that. And the idea is that the attacker shouldn't learn anything about the secrets based on observing the public part of the output. And this has been formalized under the name of noninterference. So the diagram roughly illustrates what I've been talking about. And so the second cornerstone of what we've been doing is a concept called language interface query. So traditionally, when you don't have language interface query, you're doing this kind of thing. If you want to execute some SQL, you construct a string, you pass it to some library, which then sends it to a database, runs it, and you get the result back. And this causes some issues. So for instance, you don't get safety guarantees. It might not be correct SQL code in the first place, or you might get back something that has a different type than you expect it to have. And furthermore, it's also easy to screw up security, as I said before. And one way to remedy this is to have the language provide support for database queries. So for instance, in F#, this is done by using this LINQ framework. And how this works is you get quoted expressions between these angle brackets here. And these expressions are basically a subset of F#. And then when you run this, you basically have some function that gets an AST of the quoted expression, and then you look at what it does and turn this into an SQL query. That way you can ensure that it's well typed and syntactically correct, or you can sanitize user input properly and things like that. And now our insight here is that maybe we can use the same mechanism for the outside language as for the embedded language to ensure security properties. And to demonstrate that, we have a small toy language that's roughly a subset of F#, again, based on the work from last year's ICFP. It has records and lists and higher order functions and this meta-programming facility that I just talked about. And to express our security policies, we use the type system, where we have the standard types, but it's not just about what data it is, but it's also annotated with security levels. So for instance, you could have an integer that's annotated with L, that means it's considered a public piece of information, or if it's annotated with H, then it is a secret piece of information and should not be leaked. And to give you a bit of a flavor how that looks like in practice, first I should introduce how we handle databases. So databases we assume to be a collection of tables, and the table has a couple of columns, then an entry in the table assigns one value to each of the columns. It's fairly standard. And so for the security angle, we specify the policy for the database by giving a type signature to a database. So for instance, we could have a database for a bunch of people, and then a table that states which people are couples. And then by giving types to the fields of the tables, we can, by choosing the right security level, say for instance that the names of people are private, but their age isn't and nothing else is. And one way you could use this in practice is the following code example. So first, if we want to get results of this shape, we want to put out a list of records that has a name field and an age difference. The idea being that maybe we want to collect, for some statistical reason, couples where the age difference is greater than 10. And that's might be useful because it's slightly anomalous or something like that. And then the way you do this, just in terms of code, is a fairly simple SQL kind of construction. You iterate over all the couples in a database, then over every pair of persons. You check if it's actually the pair that's being considered. And then you check whatever criterion you're interested in. So in this case, it's the age difference. And if that's satisfied, then we output that record as part of our results. And the idea about the enforcement mechanism that's also being demonstrated here is that when we annotate the result type, saying that this part of the output is considered private, then the type checker will look at the typing we gave for database. For instance, it will see that names are considered private, so this field is correctly typed as high. But however, if we were to change the typing to say that the name part is also considered public, the intuition being that this might get sent over network or get sent back to the vendor of the application or something like that, then the type checker would reject the program, since it realizes that the result, that part of the results that's being typed as low, still depends on private input, which would violate our policy. And the implementation would then reject this. And to make this notion a bit precise about the security that we're talking about, we first introduce a relation that relates values that look the same to an attacker, and that's defined structurally based on the type of some value. For instance, if you have integers classified as low, then they have to be actually equal for the attacker to view them as equal, and if they are considered high, then they might differ. Or for lists, for instance, the level would refer to the spine of the list being confidential or not. So even if you have a public spine, then the elements might still be confidential. So if you have this type where the elements are private and the structure of the list is public, then those two lists would be related because they do have the same length. But if you consider the elements public as well, then these two values would not look the same to the attacker. And the thing that we want to do with this relation is to characterize non-interference in our setting. And that's done in the following way. If we assume that we have two expressions of the same type, then they are considered non-interfering if and only if when they evaluate to some values given some database contents omega, and these database contents look the same to the attacker, then the results must look the same to the attacker as well. That basically fits the non-interference definition intuition that I showed you earlier. And the basic idea is that if you have a secure program, it should be non-interfering with itself. So if you run it with two different databases that look the same to the attacker, so the public parts are equal, then the program should always output, the program result should always coincide on public parts as well. Otherwise, the attacker could learn something about private contents of the database. And now I'll talk a bit about how to enforce this property. For that, we are using a fairly standard security type system based on FlowCamel, which does information flow control for OCaml. And so the basic insight that we had is that if the language that we're using to generate the queries is just a subset of the host language, then maybe you just need one security type system to handle all that. We have the same type system that we apply to the host language and the embedded language. And then we don't have to sort of come up with a new way to securely type SQL to ensure that there's no information leakage. So that kind of thing is exemplified by these two rules. The first rule is for the list depending construct in the host language, and the second one is in the embedded language used to generate these SQL queries. And as you see, the only difference here is the typing judgment that's being used, but the rest of the rule is exactly identical. And what the rule basically does is keeps track that the levels of the list are properly propagated. So, of course, if you append two lists, then it will reveal information about the structure of both of the lists that you're appending. So you will have to form the join of these two security levels. The join is basically just if one of them is private, then the result will be private. And the kind of soundness guarantee that we then give is if a program is well typed, then it is actually non-interfering in the sense that I showed on the previous slide. Now then, as I said, we also did an implementation of this thing. We implemented a type checker and a compiler written in Haskell, and for parsing we used this BNFC tool, which you give it a grammar of some sort, and then you get out a parser and an abstract representation of your language. And the type checker is a fairly standard thing. It's based on constraint solving and unification. And to compile it, it's a very straightforward process. We just remove the level annotations on types, and then what you get out is basically valid of F# already. And since this is a static approach, and we just do the type checking in advance and then erase all the security stuff, this doesn't have any impact on the performance when you actually run the program. And then, slightly orthogonally to that, we also extended our approach to algebraic data types, which fits quite well in this setting. So algebraic data types, of course, as I'm sure you know, are a mechanism of allowing people to define their own data structures in a very flexible way. So you can also handle recursive structures such as lists. And then we also extended our type system and the soundness proof for our extension for ADTs. And to give an example of how this looks like in practice, I'll use the example that everybody first uses for ADTs, namely lists. So if a user wants to define their own list data type, they might do it like this. A list is either nil or it's a const cell consisting of some element and then the tail of the list. And then you might want to define some operations. For instance, you could want to define this exists function here, which basically checks if a list is empty or not. So you pattern match on the list. If it's nil, you return false. If it isn't, then you return true. And the important thing here is that we get reasonable types out of our type inference when you look at the security levels. So it has this L parameter here, which is this level of the structure of the list. And the type checker correctly sees that you're only looking at the structure of the list. So this T can be arbitrary. We don't need to look at its level. But the level of the list is revealed in the result. So this Boolean will have to have the same level for security as the input list. And you can do slightly more complex things as well. You could have a union and a list appending operator. And then you also get out a reasonable type. If you take in two lists of for some element type T and some level L, and then you get out a list of the same type. And now you might wonder that this is not exactly the same type that we had in typing rule before. There we had two different levels, and here we formed a join. That's because our type inference is somewhat approximative in that regard, but since our language always allows reclassifying public information as private, this is not actually a problem in practice. You could just sort of raise the security level of one of the arguments if you have to, and then this will work. And yeah, so lastly, I'll get to the example, to a case study that I mentioned. Basic setting is a movie rental database. We took some example data from this PostgreSQL tutorial website. It's a database that has 15 tables, and it has about 1,000 movies and some rental data. And what we consider private, what we want to protect here, is the exact addresses of customers and staff. And we consider the cities of where the rentals take place to be public, so we can have some interesting predictions or some interesting statistics to collect about things. So the database basically looks like this. We have a table containing a city, then we have addresses that are in some city, and addresses correspond to some customers who live there. And so the red fields here are what we consider private, and the rest is considered public. And the customers are involved in some rentals. And what we can do with this, for instance, is to get a list of all the rentals from some cities, so we can maybe predict what movie is likely to be rented next. And this is perfectly fine because to type as low, because the no private parts of the database contents are being used in the result. But if you're doing something illicit, something slightly fishy, where, for instance, you might want to get the list of customers who rented some particular movie and try to type this as low. In reality, this might correspond to sending this across the network. Then the type checker will reject this kind of program, since it looks at the type, it sees, okay, your output string is low. However, you're actually using the customer's last name, which is a private database field. So this kind of program will be rejected, as it should. So this gives some evidence that our approach works as we intended to in practice. And yeah, as a summary, we gave a lightweight framework for tracking information flow for programs that also use database queries, and we do so with very little extra work, since we're reusing the same type system as already exists basically for ordinary languages, ordinary code. And yeah, we give a formal treatment of our security type system and show that it ensures non-interference. We provided a proof of concept implementation that's producing executable code and handled ADTs and pattern matching. And lastly, we gave an evaluation using this movie rental case study. And what we're looking at now is also handling at one of the missing pieces for real web applications, namely client-side code, some JavaScript that's communicating with your server part of your application. And yeah, it would be nice to then finally close the gap and have a real end-to-end mechanism to ensure security. And that's all. Thank you for your attention.
Yeah, question?
Hello, Edward Yang from Stanford University. So I guess I have two questions. One, do you support more complicated labeling schemes than just low and high?
So we use low and high to demonstrate the process, but it generalizes very easily to arbitrary lattices. So
okay,
yes,
so then my second question is, so normally when you have a web application, you want a policy like this data is private for some user. And then if I have a chat application, say I have a database that has rows for messages that people send to people, now I want my security policy to depend on who the recipient of the message is. So can you do something like that in your system?
No, in our system at the moment that doesn't work. Instead, it would depend also on the particular data that you're handling, not just the shape. You're not just can't just classify. At the moment, we're just classifying the rows, the columns of tables. So we're not supporting it.
Okay, thanks.
Over there.
I'm John Sterling from Olive Cloud Systems. First of all, very nice work, very cool thing. So it's kind of interesting. So like you had that E tilde E thing earlier. So something is good if it's non-interfering with itself.
Yes.
It's interesting how that sort of comes up a lot of times, because that's the same idea as in type theory. Something is considered the value is extensional if it's reflexive in the equality relation of its type. And I was sort of wondering, because I could sort of imagine a situation with what you built where I might want to come up with like a non-trivial line of reasoning to show that something is secure, as opposed to it's like merely syntactically non-interferent. So I wonder, it might be interesting to think about sort of embedding this into a computational logical framework where you can carry out those arguments when the type checker can't figure it out for itself.
Yeah, exactly. As you said, with this kind of type system, it's sound, but it's not very precise. There's lots of secure programs that you just can't figure out that they are secure.
Thank you.
So yes, it's very.
Alexei Romanov, Huawei. If you could turn back to the slide with exists function. Right, yes. Its type seems to say that the level of result only depends on the list itself, not on the level of its elements.
Yes, that's right.
Okay, but could you write a function which would depend on the elements of the list?
Yes, you can, and then the level of the element will be joined with the level of the structure of the list in the resulting type.
Say.
So the cool idea here is that if you can manage to make a database, say, look like an ordinary programming language, then you can take security techniques developed for ordinary programming languages and apply them to a database. And when we presented the paper last year, at the end of it, one of the points we noticed, well, we don't deal with things like aggregation, but that's okay, because the basic technique is normalization, and you can just check by experiment that in practice normalizing doesn't break things. So we still had an improvement to Microsoft's SeLINQ system. But now you're trying to depend on it looking like a programming language, and we didn't do the theory of aggregation. So is that a problem? Do you deal with aggregation?
Question. I think I haven't thought about it in those terms. So I would have to think about it.
You didn't want to count the number of cities in which somebody did a particular rental.
Yeah, no, we're not considering that at the moment.
Okay, so aggregation worked in practice, but now we have a really good reason for doing it in theory. Okay.
Any more questions? Then let's thank the speaker again.